Yeah, so we're gonna get started. Thank you all for making out today. It's like week 7, so I hope your course is kind of going okay. And yeah, let's get started. So just a few announcements. The first software module, I released it probably like a week or 2 ago. So get started working on that if you haven't already. But also you can just wait until the work session's coming up. There's gonna be one next week, and then one I think week 10. Upcoming events. I forget exactly where I was going with that, but I'm pretty sure I just meant outside of RAP. So yeah, we have the 2 work sessions for RAP, and then outside of that, there's like a KBBQ thing tomorrow. If you guys do one of that, and then probably some other stuff.
Where are you going?
Probably, yeah, I haven't decided yet. Okay. So yeah, I'm gonna go over like a recap of lecture 1. I'm gonna go into it in a little bit more detail than I normally would because unfortunately I wasn't able to get the lecture 1 recording up. So we'll start with that, and then we'll talk a little bit about digital filtering, then move on to a discussion of match filters, and finally we'll end off by discussing synchronization. Yeah. So recap of lecture 1. So very briefly again, lecture 1 can be divided into the 6 stages you see on the left. So we have the bit generation stage, and then all the rest we'll kind of get to as we go along here. Yeah. So the first step to communicating in RAP is we begin with a sequence of 6 characters, which are each mapped to a bit sequence, right? So in general, we can choose any mapping of bit sequences to symbols. In RAP, we choose BPSK because it is simple to implement and it's robust. So all that means is that 1 corresponds to 1, 0 corresponds to -1 as shown in the diagram. When we want to actually transmit a pulse, you can imagine transmitting some sort of waveform. If we just have our discrete symbol sequence, that's not enough to transmit because it's very high bandwidth. That's one reason. The other reason that we want to kind of pulse shape this before transmitting is you can imagine that on the receiver side, if we receive something like this, it's not resistant to kind of timing errors, right? If we sample slightly off anywhere, we're going to miss the symbol entirely. So for those 2 reasons, we want to choose a pulse shape that we can use to transform this impulse train into a pulse that kind of smoothly changes from one symbol to the next. The way we choose that pulse, there's only one kind of simple criteria it needs to satisfy, which is basically this right here. So at time t equals 0, the symbol or the pulse shape has to equal 1, and periodically it should reach 0. So the idea there is that when you kind of send one after another, that at the instance we care about, right, at the sampling period, the neighboring pulses will all go to 0, and we end up with no interference there. But you can see how in general, in the middle, we're going to have some sort of interference because all of the kind of each component from neighboring pulses are going to add together. So in the diagram here, I just have 2 examples of pulse shapes. The one on the left is a rectangular filter, and the one on the right is a bunch of sync pulses. So yeah, the kind of goal again with pulse shaping is kind of twofold. First, we want to minimize inter-symbol interference, which you can imagine is kind of windowing the pulse in time, right? Because if it's windowed, as in this case, then you can see that neighboring pulses don't interfere at all, which is good. The other goal we want to do is window it in frequency, right? So we want our symbol to be band limited. That's the whole reason why modulation is useful. It's because we can control the frequency range that our symbol or that our message exists in. Now those 2 trade off with one another. So the rect is kind of at one extreme, and the sync is at the other extreme. Last lecture we discussed the shape that we actually end up using, which is a square root raised cosine. I'll talk a little bit more about that later on, but yeah, in this diagram here, we just have an example pulse shape. This uses the same pulse shape, so you can see kind of how that sequence maps to an actual pulse. And you can also see now that if you are slightly off, right, timing-wise, it's not going to matter that much because you can still extrapolate what the symbol should have been. Yeah, the other thing that I'll kind of mention is that I didn't discuss this in much detail last lecture, but pulse shaping can actually be done in multiple stages. We'll discuss why we might want to do this later on, but for reasons, yeah, again, that we'll go through later, we take the root raised cosine filter and we'll apply it both on the transmitter side and to the received waveform on the receiver side. That means that the overall pulse shape is actually the frequency kind of spectrum of the root raised cosine multiplied by itself, right? Because we convolve with the root raised cosine twice. Yeah, are there any questions at this stage? Okay. And yeah, once again, just the reason we use the RRC pulse shape is because it has a relatively steep roll-off in time, while also still being relatively band limited. So here's a diagram of what that looks like. You can see that in general, as the pulse kind of becomes, how do I say this? The faster it rolls off in time, the more kind of spectral leakage you have, right? Okay, so the next step we discussed after we have our received, or after we have our pulse-shaped signal is modulation. So all this is multiplying our signal by a cosine or sine, and all it does is shift our frequency, and shift the spectrum of the signal to be transmitted, right? So here we just have a cosine at a very high carrier frequency, and its transform is just two deltas here. So when we multiply by the cosine, it just corresponds to convolving our spectrum at baseband with these two deltas, which will move a copy to positive carrier frequency and minus. Yeah, so this is kind of illustrating the process I just described. And yeah, at a given frequency, another thing I discussed last time is that we actually have two orthogonal carriers that we can use, which is important because when we transmit symbols, right, in general we have in phase and quadrature components. So this scheme we use, BPSK, the quadrature component is always 0. But the reason why we kind of want to do this is because you'll see later actually that we need both the I and Q components in order to kind of properly synchronize the transmit side and the receive side. But the takeaway from this slide is basically that if we, for instance, multiply an in-phase component by a sine and the Q component by a cosine, we can add the signals together and then transmit it. And in general, when you add two signals together, you lose information about each signal individually. But if you demodulate using the right carriers, then you can actually extract the I and Q components separately. Are there any questions about how this diagram works or any of the previous steps? Okay. Oh yeah, sorry. One other thing that I'll mention here is that we include these filters because if you imagine what the frequency domain looks like for this channel, for the system, then when we first multiply by, let's say, a cosine, then we have two copies at positive minus FC. When we multiply again on the receive side, then those two copies each split to two of which combine at baseband, and you'll end up with high frequency artifacts as well. So the low pass filter just gets rid of those. Okay. So yeah, we also discussed complex baseband. All it is just a shortcut that we use to, number one, represent these kind of wireless systems. And it's also useful because it lets us easily see the effects of different kind of non-idealities, right? So we discussed 3 sources last time, there are many more. But actually we're gonna address each of these 3 this lecture. But the first thing that we notice is that there's gonna be some amount of noise added to our signal. We'll discuss that first. There's also going to be, in general, some sort of frequency offset and phase offset, right? So we have 2 separate carriers on the transmit and receive side that are generated by circuits. And because the system is wireless, they can't communicate. So we have no way of enforcing that those 2 cosines, for instance, need to be synchronized. So we saw the effects of that last time. So using a QPSK scheme for this example, or QEM, we have 4 symbols. I don't know how easy it is to see, but they should just be here, kind of in this square. In the diagram on the left, we have a frequency offset. So all that means is that X, in this equation here, X represents kind of the received waveform, the pulse-shaped waveform, right? So all we're doing then is then sampling X at certain times. And in general, if we sample at the right times, we should just receive our symbols back, right? Now, if we multiply it by time varying complex exponential, all that's gonna do is rotate the received symbol by some unknown amount, right? Depending on time, around the complex symbol, which is why we end up with a constellation like this. If we have the same frequency on the transmitter and receiver side, and you have a fixed phase offset, then all that does is rotate the constellation by a fixed phase. But yeah, you can see how, in general, this would be problematic if you have more complex modulation schemes. Yeah, another topic that I want to discuss before moving on to the new topics, kind of important for last lecture, but I didn't go through it in much detail, and that's the effective sampling. So we've discussed the relationship between an analog waveform and its discrete kind of counterpart, and we haven't discussed that in very much detail. So right now I'm going to go through what exactly the correspondence is. So the basic idea is that when we sample our signal, we're copying its spectrum at intervals spaced by the sampling frequency. We're also scaling the copies. That doesn't really matter that much, and I have a diagram kind of pretty soon. But Yeah, so intuitively, we kind of know that when we sample our signal, the faster we sample, the more data we have about our signal, which is good. But now we're going to see kind of exactly what that means. Okay, so let me explain what's going on here. Let's pretend that our transmit signal, X, just has this spectrum, this triangle here, red one. When we sample it periodically, we're going to get a bunch of copies, starting with this one and going all the way to infinity. The copies, as I mentioned, are spaced by the sampling frequency. And now we can kind of look at what happens, what effect the sampling frequency actually has, right? So who can tell me what will happen if we raise the sampling frequency? Like, what will the diagram look like?
Like each of the yellow triangles is now like has a blank space in between them.
Exactly, yeah. So now we're gonna have some space between each of the copies, which is good. And in the opposite case, they're gonna start to overlap, which is a phenomenon we call aliasing. I forget which slide I had that on. I think here. Yeah. But you can see basically that if we shrink the sampling frequency, then these are going to overlap, and then the high frequency components, notably at baseband, right? The low frequency components from this copy are going to alias into the high frequency components here, and we're no longer going to be able to have information about what those high frequency components are. Yeah, so in general, we want to sample a signal with a maximum frequency component at double that maximum frequency component, right? So if you have a 2 Hz signal, the minimum sampling rate that we want to achieve in order to perfectly reconstruct that signal is 4 Hz. Yeah. So let's kind of go through an example. Here's a cosine 2 Hz. Yeah, here we're sampling it at 1 Hz, looks like, right? I don't know how easy to see the axes, but we just have sampling points there. So now I'm going to ask you to kind of redraw what that cosine would look like in this diagram, right? There's an infinite number that you could draw, because you could draw any number you can imagine, like very high frequency cosine. Now we're interested in kind of what the lowest frequency that we want to draw is, right? So you can draw, yeah, you can draw a straight line through it, 0 frequency, or you can draw 1 Hz. Signal. We know the correct one is 2 Hz, so let's kind of look into what's happened here. Oh yeah, this is kind of not easy to see, but I've just put in a bunch of extra cosines at higher frequencies. The one that's highlighted that you can see is the 2 Hz signal, which we know is right. So yeah, what's happened here is that when we sampled our cosine, right, at 1 Hz, we have this original copy at 2 Hz and minus 2 Hz, and then you can imagine scaling that number 1, and then copying it everywhere. So these two move this way, and then they also move the other way, all to infinity. And you end up with this impulse train in frequency, spaced by 1 Hz. So now you can see why we were able to look at the train of samples and say, okay, we can draw a DC component, 1 Hz, 2 Hz, etc. It's because this spike in the center corresponds to DC component. Outside of that, any pair of impulses at the same frequency is a valid cosine that we could draw, right? Notice that filtering doesn't help us here as well, because if we say cut off all of the spikes here and here, that still leaves 3 candidates for what we could draw. So yeah, if we sample it at 5 Hz instead, notice that that's now above the Nyquist rate. So if you go here, now each of the copies is spaced properly, there's a gap, and we can readily identify that, okay, if I ignore all the high frequency stuff, then this is our correct frequency component. Yeah, that's it for the recap. Are there any questions at this stage? Okay, great. Yeah. So filters, basically, when you think of filters, you might first think of analog filters, which you've seen in all your circuits classes, and all they do is just alter the frequency components of a signal to a desired effect, right? So you can enhance and attenuate different components. And the output signal is found basically by just multiplying the frequency response by the input signal spectrum and then taking an inverse transform. They're implemented by circuits, as Seth will talk about later. But yeah, so here are just a few types of filters that you've seen before. Yeah. Does anyone want me to go through this? Okay, cool. So yeah, now let's talk a little bit more about digital filters. They're used everywhere, as I'm sure my 113 fellows will know. But yeah, so let's talk about exactly how we design them. In general, when we implement difference equations, right, all that comes out to is a bunch of multiplications and additions in hardware. Difference equations are one tool that we can use to directly implement digital filters. And the takeaway is basically that all we need to implement a filter is a list of coefficients and either some amount of the input signal and then some history corresponding to the output signal, right? So that would, this part of the diagram here represents feedback because we take the delayed values of the output signal, right, and feed that back to get the new value. And then we're taking some amount of our input signal, and that also kind of adds to get the output. Yeah, there are two main classes of digital filters: infinite impulse response, which are impossible to implement, so we're going to skip them, and then finite impulse response, which we are interested in. These, again, only require a list of filter coefficients to implement. Another thing that I should mention quickly is that IIR filters, in general, can achieve very high roll-off, but they're usually unstable to some extent because they have this sort of memory effect where if your input, let's say, was non-zero at some part and then zeroes out, because you kind of keep track of all past values of the output, there's no guarantee that the output will also go to zero after some time. So yeah, in terms of designing an FIR filter, there are many ways to do this, but the simplest is basically to begin with a known filter shape in continuous time, and then basically take a discrete sequence to map to that analog filter. And from there, because we want a finite number of coefficients, we're going to want to window our filter. And then from there, we obtain an FAR filter. You just have a list of discrete components, right? So I have a question here for 5 points. Will the frequency response of the digital filter exactly match the response for the analog filter if we use this technique? And I'll give you a hint. What happens when we window the signal time? And then think about what happens when we sample a signal. So, to kind of go through this a little more carefully, when we sample a signal, remember that I talked about earlier, we just copy the spectrum over and over to infinity, right? That's number one. Number two, when we window a signal in time, if it's fully windowed, then it has infinite bandwidth, right? So if we take that spectrum now and then copy it over and over, then there's going to be some level of interference, right, between neighboring copies of that spectrum. Which means that in general, the frequency response of the digital filter will not exactly match the analog response. Which in practice won't matter, but it's nice to know, I guess. Yeah. Okay. The next thing I want to talk about is time constants and bandwidth. So in general, we know that the faster signal varies, the higher its bandwidth, which means that, again, sampling faster lets us capture sharper transitions, which in turn yields a more ideal Fourier transform, right? So you can just see a couple of examples here. By the way, the order in these two expressions here just means the number of coefficients that we have. Yeah, so here's another couple of examples for the RRC filter. So yeah, if you just compare the axes, you can see that the one on the next slide has a much steeper like roll off. And yeah, the other thing I kind of want to discuss, because it's kind of easy to get this confused, is again the relationship between continuous and discrete time, right? So when we have a discrete sequence, we lose all notion of what actual time we're concerned with, which becomes important because when we think of like what happens when we actually apply a digital filter, at the end of the day, right, we're just convolving two discrete sequences. So the important thing to remember when you design filters in the digital domain is basically that you keep track of what your like sampling rate is and how many symbols you have, right? So what I mean by that is actually best explained in a diagram. So I'm going to skip this slide for now. And basically, this purple signal represents some signal that you just want to apply a filter to, right? So this will have some sampling frequency associated, and then when you design your filter, right, you're free to choose the coefficients and everything, and you also want to make sure that the frequencies you choose, the sampling frequency, span, whatever parameters you use, you want to make sure that your resulting signal will line up with your input signal in the way that you want. So that's something that you want to kind of carefully go through when you go to design these filters. Okay. Yeah, I'll go through this and then we'll take a short break. But the next topic is SNR filtering. So yeah, I mentioned earlier that when we apply a pulse shaping filter, we can break it up into multiple stages. So yeah, I guess I just answered my own question here, but the idea is basically that the receive filter and the transmit filter will both use the RRC filter. And then from there, you can imagine that at the output then we get our overall pulse shaped signal. In the case that we don't have any noise. So yeah, our received signal is basically a combination of, if we have our non-pulse shaped signal here, so just a pulse train, involved with this, right, and then we modulate it, in the case that we have no noise, we'll perfectly recover S convolved H sub T. And then finally convolved with H sub R. So that's what the first term is. The next term is just the result of additive noise. So if you remember, we'll have S convolved with H1 plus noise by itself, and then both of those will end up being convolved by the second filter. Which means that the resulting signal we care about, right, our fully pulse-shaped symbol train added to this noise component. So the idea behind maximizing SNR is basically just maximizing this component of the receive signal relative to this one. Okay. So yeah, a question that we might ask at this stage is basically like, if we kind of break up, you remember that when we choose a pulse shape, we're choosing a specific waveform. So now the question is, if we break up the pulse shaping process into two stages, will the two pulse shapes that we choose for each filter, will the result of that still satisfy the Nyquist criteria? And with some thinking, the answer is yes. The example that you can think of is the sync function, right? If you convolve it by itself, with itself, then in frequency domain, you send it with a rect again. So convolving it a number of times just gives you back the same thing. So the takeaway from this slide is that yes, it's possible to divide up the pulse shaping process into multiple stages as we've done here. Yeah, so, yeah, what's up?
Can you clarify what you mean by convolving it with itself here?
Yeah, sure. So, I'm gonna borrow that red marker since I know it works. Thank you. Yeah, so what I mean is this, where we have a sync in time, right? And then its frequency domain response is just a rect.
Okay.
So if we convolve it by itself, then that means that we multiply this spectrum by itself as well. If this has amplitude of 1, we end up with the exact same thing. So we can convolve this any number of times, and then we just end up with the sync again. Yeah.
Is there any requirement that you actually have to convolve it with itself? Could you convolve it with a different H2 and shape differently?
Oh yeah, yeah. The only requirement is that the overall pulse shape satisfies the Nyquist criteria. So, yeah. So that question actually is the reason why like people have to go through the headache of figuring out what the ideal pulse shape is and how they arrived at the Rugrex cosine. So yeah, in frequency domain, the overall pulse shaping filter we're using then is just the raised cosine filter, and we get that from just convolving two RRC filters, which means that half the filtering is done on the transmit side and half on the receiver side. Another thing you might notice actually from this diagram here, I guess I haven't made it clear, but there's no low pass filter anymore. So why might that be the case? I'll give you guys a hint. Remember that the RRC filter looks kind of like a sine but messed up a little bit. In frequency domain, it has a sharp roll-off, right, in frequency.
Yeah, so like the sharp roll basically has active with
Exactly, yeah. So the nice thing is that the RRC actually doubles as a best filter. So, yeah, we don't need a separate one. But yeah, so some pretty smart people have figured out that the RC is the ideal, or is one very good option for the pulse shaping process if we split it into multiple parts. Which means that the takeaway is, again, that by splitting the pulse shaping process into two stages, we're able to maximize the SNR. And from this expression here, that this part that we care about is very large compared to that part. So that actually addresses the very first problem we discussed, right? From the hardware, from the channel, our signal can be distorted in a number of ways. One of those just being random noise. So this is one way to kind of improve that issue. And yeah, before we go into synchronization, we'll take a quick break so that my phone doesn't collapse like last time.